So I'm going to talk about Bayesian neural networks, a bit about my implementation in STAN, and then some results. And I specifically worked on nonlinear univariate regression. So a classical neural network can be thought of as a complicated nonlinear layered function, or a nonlinear layered model. So there's an input layer that has nodes for each that has a number of nodes equal to the dimension of the input. So if you're doing univariate regression, you have one input node. If you're doing bivariate regression, you have two input nodes, etc. You have an output layer, which gives you the output, and then you have these intermediate hidden layers, where the hidden layers can be any shape and any size. You could have 80 hidden layers with one neuron each, as it's called, or one node each, or you could have one hidden layer with 80 nodes. Specifically for my problem, I had 3 hidden layers with 3 nodes, 8 nodes, and 3 nodes. And then, of course, it was univariate regression, so I had one input and one output. The way each layer is linked is with a nonlinear function applied to a linear combination. So we have these W weights and B biases. Think slopes and intercepts of linear regression, and then we just get the next layer by taking the tanh of that previous linear combination. Combining all of these gives a very complicated function, but it has some nice properties. In particular, it's known to be a universal approximator. It can solve essentially any problem, any regression problem or any classification problem. It's a little more complicated because you need sufficient numbers of hidden layers and sufficient sizes of those hidden layers, but we know that in theory we could find a certain what's called a neural network architecture that could solve a given regression problem. So for my problem, I had 58 parameters, which are these weights and biases, where each element of a weight was a parameter and each bias was a parameter. And then I chose standard normal priors on each of the parameters. And while that might seem to be too informative of a prior for this problem, because we don't know what sort of priors might work well, it's actually reasonable, because the tanh function has a range of -1 to 1. So if I had a very large parameter values, they would just be truncated inevitably, or the output when I apply the linear combination. Let's say the bias, right, is 150. Well, that's kind of useless because it just means the output's going to be 1 every time, right? Because tanh of 150 plus something small is going to be 1, and vice versa. So it's actually reasonable to restrict parameters to a fairly narrow range. But I had no reason to believe that they should be any more general than just normal near 0. So so classical neural networks are trained with gradient descent, which is just a regular optimization technique that gives optimal parameters. In Bayesian neural networks, however, we want to find optimal distributions of parameters, or distributions of parameters around the optimal parameters. To do that, I use Markov chain Monte Carlo, specifically the no U-turn sampler Markov chain Monte Carlo that's built into STAN, a Bayesian computational package. So these are some of the trace plots, just a representative sample of the trace plots for when I did regression with y equals x squared, y equals x cubed with the normal prior, and then y equals x cubed with the Cauchy prior. So we see that the y equals x squared case mixed very well, and we'll see that this had a really good effect on the posterior predictive distribution graph, though in the first bias turned out to be multimodal, but it didn't have any issues. For y equals x cubed, the mixing wasn't quite as nice. There's some of these parameters that did mix well, like parameter 8 in the Cauchy prior, but some of them, like parameter 1 in the Cauchy prior, look almost like random walks. I didn't have time to investigate this fully and try and get these to mix, but the posterior predictive distributions ended up working out either way. So in these graphs, the red dots are the actual data points. I had a training and a test data set, which were each half of the data set. I sampled it using R. The blue and the green give the 10% and 90% percentiles of the posterior predictive distribution, so that's like a 80% credible interval, and then the black dots are the mean of the posterior predictive distribution. So a classical neural network would give us just those black dots, or something similar to those black dots, but a Bayesian neural network gives us this nice credible interval. And it has a few nice features. We see in this, especially in the testing of the y equals x squared case, we see that really all but 2 of the test points are contained in that credible interval, which is just a really nice feature because it shows that, and it's pretty tight, right? Even in the areas where all of the test points are contained in the interval, it's not like the interval is really large. It's tight around the data. So it gives us a good measure of the error or the inherent noise in the data. And that's one of the big benefits of Bayesian neural networks. Unfortunately, this didn't work out in the y equals x cubed case. There's a few possible reasons for this, including the chains not mixing well, and the data sets just not having enough noise. It seems like they didn't, for some reason, the noise didn't scale as well as with the y equals x squared case. Or, yeah. So for the, I also tested with the Cauchy prior, and I had the same results as with the normal prior. I also tested sinusoidal regression. In particular, this is y equals sine x. We see it's a bit complicated to look at, but we do see that the black and red dots align pretty well. Obviously, our model is always going to be an approximation, but it seems to be a good approximation. We also see some interesting edge effects that at the end of that the green and the blue really pick up at the edge of our interval as the minimum and maximum of the sine function, which is just an interesting observation that they pick up on that. I also tested a real R data set. This is the CO2 data set, which is a data set of carbon dioxide observations over time. And we see really that the Bayesian network just recovered the classical regression. It really picks up the center of that distribution of the data. Unfortunately, like in the x cubed case, the quantiles, percentiles didn't really work out quite right. I need to investigate this more, but I didn't have enough time. Now, while these worked well, there are some drawbacks, and these are really drawbacks of scale. Because I used Markov chain Monte Carlo, I have to do repeated samples, and these repeated samples require evaluating the neural network feed-forward function, right? That tan h of tan h of tan h that I showed earlier. Because I have to evaluate the model many times, and potentially with a large data set, you end up with multiplicative scaling as you add more parameters, and you end up with compounding scaling. So as we add more parameters, right, we need to do more Markov chain Monte Carlo sampling because we have to sample each parameter. As we add more parameters, there's less interpretability of the parameters because we can't really keep track of a single parameter when there's 5 million of them. There's also these non-parameter choices. We have to pick how many layers we want, the sizes of the layers. As we add in more things, add more choices, like more parameters, etc., our training is going to slow down. When the training slows down, then it's harder to make these non-parameter choices. This leads to a lot of issues, especially in more complicated high-dimensional problems. There's also some further exploration we can do with Bayesian neural networks. Specifically, there are these methods called variational Bayesian methods, which are alternatives to Markov chain Monte Carlo that scale much better. There's extensions to higher dimensional data, so bivariate regression, trivariate regression, etc., predicting multivariate functions. There's classification, which is a well-studied extension of classical neural networks that can easily be extended to the Bayesian case. And then there's also just this like investigation of the MCMC convergence. Like, why did some of the chains not mix well? How could I get those credible intervals to work better, etc. So thank you for watching my presentation.